So I was asked about a pretty tricky problem. So I'll just show you a part of the problem. So there was a problem with modeling that had to do with a highway, and it talks about like this is the construction of the highway, and then finding some particular distances between different parts of the construction of this model. So what I want to do is actually, before I get into this problem, I want to talk a lot about how this particular model is constructed, because if you don't understand this is like set up in a very, very particular way for this problem to work out like it does. So I really want to take a moment to explain all of this, and then I will break down kind of how to solve this problem. Okay, so the basic premise of this is that there's a basic basic highway curve connecting two straight sections of road may be circular. So what does that mean? So pretend that I have a straight section of road here and a straight section of road here. And so to connect them, I'm going to have something that's kind of circular. So we are focusing on this connection, like if you were to extend these two pieces of road. We're talking about something very specific. And so baked into this, something that's kind of assumed then when it says the road may be circular. So this extension, the way that this is kind of going to work is it's talking about like there's this underlying circle here. And so you could, in your mind, extend this entire circle. Okay, so that is what it's talking about when it's referencing that this may be circular. And this is important because if we have a circle, there's an implication of a radius. And once we have a radius, then we can start bringing in angles and stuff. So for now, all I want you to remember is that there's an implied radius here. I'm going to keep coming back to this idea because we have more to build up with the construction. Okay, so the next thing the problem talks about is that we let points A and B mark the beginning and end of the curve. Now, the way that A and B are selected and the way that these straight lines are constructed, as you see here, this is actually pretty strategic. And I'm going to show you why as we keep building up this problem. We're also going to have a point C. So the point C is going to represent the point where the two pieces of road would meet if they were extended. So remember, I showed you those two slices. If you thought about extending them, the point where they extend up to would be this point C. Okay. All right. So let's keep going with this. So I want you to, in the back of your mind, imagine that you have this border of this circle running through this road like this. I'm going to reference this a few times. And so from here to here, I'm going to assume that there's some sort of radius, okay? Now, if I know that I have a radius from here to here and I have this circle running through like this, I could also extend this concept. So I have a radius here, I have a radius here, and I have a radius here. So here's that circle, and that's how it's going to extend, okay? All right. So let's keep that in mind. And I'm going to refer to different placements of where this radius is, depending on what I'm asking for the problem. So all I want you to remember right now, I'll continue to label this and remind you of this. There is the circle here, so we have these different options for the radius. Okay, so the other thing with how this particular model is constructed, like I said, this A and B is very strategic in how the model is made. So we assume that where the radius meets these points, this is something that is just assumed in the construction of the problem. The radius meets this line segment in such a way that we get a right triangle. And knowing that this is a right triangle is what's going to make this problem so much easier. If we didn't have this right triangle, this problem would be really tough. Okay, I'm going to reference the fact that these are right triangles later. I'm just mentioning that now, and I'll remind you of that information when it's pertinent. Okay, so we have this radius that we talked about. And so since I have a radius here and a radius here, so from the way that this shape is constructed and the fact that I know that I've got this circle here, I know that there's a central angle theta. And I'm going to assume that this line segment here perfectly bisects theta. So I can also assume in the model, I'm like told this is part of the information that's given to me. This side is theta over 2, this side is theta over 2. So there's a lot of information that's kind of handed to you in the construction of the model. Okay, the last piece of information that I want to include here, I want to include these points P and Q, and I just want to make sure you understand them before I go into parts of using them. So P lies on the line segment that's going to connect A and B, okay? It is not part, it is, so from 0 to P is not the radius. Where the radius is actually going to be from, or not 0, O to Q. So remember we had that underlying circle that kind of motivated all of this. So Q is going to be where the center comes out to the radius. So just remember that for now, and I will refer to that later, and I will keep reminding you that we have this circle going from this A to Q to B type construction. Okay. So now I can get to the actual problem. So there's a problem that says find the distance between A and C if the radius is 925 feet and theta is 34 degrees. Okay, so we want this little section here. We want that distance, okay? So a couple of things we got to remember here. We have to remember that where this radius meets the line segment, that forms right angles. So I have right angles here and right angles here. And that's important because then what that means is that I can assume, even if it doesn't totally look like it from my drawing, if I'm told that I have a right angle here, then I know that this is a right triangle, which then allows me to use all my trig functions. So since I can use trig functions, that's what's going to allow me to most easily find AC. Okay, so now just to remind you of what's going on in this problem. So theta was 34 degrees, so this whole thing is 34. So my theta over 2 is going to be 17, and this radius here was 925. So I have this angle here, I've got a right triangle, I know this side, I'm trying to find this side. So what trig function is going to utilize this side and this side? Well, that's going to be tangent. So I can take tangent, I can take opposite over adjacent, so AC over the adjacent side will be R. Okay, because remember, this is where your right angle is, so this will be your hypotenuse, okay? So just making sure you remember the construction of this. So this is where the right angle is. All right, so now I've got this all set up, and my R, remember, was just 925, so I can plug that in, and now bada bing, bada boom, I can go ahead and finish the problem. And if I want to use, say, 2 significant digits, then this would just be 280 feet. Just depends on what format of the answer you want. Okay, so the other question associated with this problem is to find an expression in terms of theta and R from P to Q. Okay, so to do this, so remember that Q lies on the outline of this circle. That's why I've made a big deal about that, because this gets really overwhelming. So now I want to think about the fact that from O to Q, this piece here is my radius, okay? And so if I'm trying to find this little distance PQ, then to do that, what would be helpful would be to think about how could I describe this length from P to O? Because I know Q to O, or O to Q, this whole yellow part, right? This whole yellow part is R. I'm trying to figure out this little piece here. So the way I would like to describe this length here that I've circled, I want to describe that as R minus PQ. So why am I labeling it that? So remember the goal of this problem? We're trying to get everything, we're trying to figure out an expression for PQ, and we want to only use R and theta. So I really want to stick to either using the PQ line segment or R or theta for anything that I describe this problem with. Okay, so this length here is R minus PQ, and so I'll label that as you see. And the goal is to write an expression only in terms of theta and R for PQ. So the other thing I want to think about now is that I do know one other length, or like one other length that would help me in this case is R. And by the way, those numbers that I had earlier, like we're discarding those. We don't care about those now. We're trying to keep everything just in these general terms of R and theta. Okay, so think about this now. I know this length here, I know this length here, and this part right here is a straight line, and then this here is perpendicular to that little blue straight line that you see there. So this part here is a right triangle. You see what I'm saying? So now, once again, like we're really looking for where the right triangles are so that we can use a trig function. So now I know that I've got, so theta over 2 here, right? So if I know this side, I've got some way to label this side of the right triangle, and I call this side R. Well then, so in this case, this is what I'm viewing as my hypotenuse, and this part here is going to be my adjacent side. So just to, so cosine, right, is adjacent over hypotenuse. So to set this up, okay, so here's my adjacent side, r minus pq over r. Now, in case you're wondering, like, wait, I thought r was the side of a different right triangle. So the other right triangle came out here to the green line. That's what we used for the last problem, and now we've created a different triangle. So this is no longer, this is no longer the side with the right angle, because I'm now using a different side. So I've like changed the triangle. So you have to kind of get in your mind that we've switched to a new triangle. So adjacent over my hypotenuse. Okay, so now I've really got everything that I need, because I wanted to write an expression in terms of PQ. So now I can really do this, right? Because I have everything in terms of cosine functions and theta and r. So I can just solve for PQ. So I'm gonna just multiply both sides by r, so I get this, and then I have that negative PQ equals r cosine theta minus r. And then I can divide everything by -1 and just flip the order. So PQ is gonna be r minus r cosine theta over 2. So that was kind of a complicated problem, and I think what is so complicated about this one is that you have to have you have to really understand kind of how the model is constructed. So hopefully that was helpful. If it was helpful, consider leaving a like for the video, and I will catch you guys next time.